Recall that a basis is something we can just think of as a linearly independent spanning set. And that's a little bit more than something, just the way we think about it. That's pretty much the definition, but you gotta say a basis of a subset or of a set and name it and everything. And your book will give you the precise definition, but that's really what it is. It's a linearly independent spanning set. We don't say spans what, but whatever it spans, that's what it spans. Okay, and that's easy to fix, easy to fill in. Okay, so a basis is linearly independent. Now, what does it mean to be linearly independent? Well, we should be very familiar with that by now. It means that only the trivial linear combination is equal to the zero vector. Now remember, we write out a linear combination of the vectors. A linear combination, of course, is a sum of multiples of the vectors in the set. Okay, and a basis is a set. You know, again, I'm not being specific with the definition, but these are the essentials. Okay, so again, a basis has to be linearly independent, meaning only the trivial combination is equal to the zero vector. A linear combination is a sum of multiples of the vectors in the set by the scalars. So here's a typical linear combination, and we test whether that can be equal zero if there's anything but in any case other than when all the C1 through Cn constants are zero. Obviously, if all the constants are zero, then the sum of the multiples is going to be zero. But again, then the condition is that this is equal to zero if and only if the C1 through Cn are all zero. No other way for it to be zero. That's equivalent to the definition people wanted to give, that nothing is a linear combination of anything else. And that's again the way we think of it. This is a better way to write it out if we're going to try to prove anything, because this leads us directly to augmented matrix or a matrix equation. Okay, so again, if this is backing up, my statement is didn't really hold up. The set V1 through Vn, and we would write the set, you know, braces Z1 through Vn and so forth. Looking for a verb, gives us the matrix V1, V2, V3 up through Vn, where this matrix, as we know, consists of the columns V1 through Vn. In other words, we express the V1 through the Vn as column vectors. So, if the set is linearly independent, what happens is when you reduce this matrix, it doesn't end up with a row of zeros. So I could say, when reduced, this matrix doesn't end up with a row of zeros. Now that applies if the V1 through Vn are, say, vectors in Rn. Okay, because we just then put the column of numbers for each vector in the matrix, and we have a matrix. If the matrix doesn't reduce to the zero vector, then we know that the set is linearly independent. Because if it reduces to anything but with a row of zeros, and that's really, you know, I'm going to start this thing over. I like the way it's developing. Okay.